Good morning, everyone. I hope all of you are doing fine and well and ready to dive into learning something new today. And today we are going to see just a manifestation of what we were talking about, that what is inside my flash memory or USB or SSD. What is inside our flash drive? That is the question we are asking, and it's not a new thing. We have talked about it, but now we are going to look at deeply, because we talked about this thing when we were talking about different avatars of MOSFET. So it's not a surprise that you will find a brother or a cousin of MOSFET inside this flash drive. How does this cousin look like? So we already talked about it a little bit, about the structure, that to store or to bring the capability of having your data stored, right? Because we are not putting any capacitor here like in DRAMs. This is your normal uh, MOSFET. So what do we do inside this MOSFET is, we put in, rather than putting the metal there, we put in first a floating gate. Floating gate means it's a material which is floating in between. There is potential not directly applied to it. That's why it is called floating. Then there is another oxide, and then there is whatever your metal or whatever terminal you are going to apply, right? Some highly conductive material where you apply this voltages. And the source drain is very much the same, which we have seen, right? And we also discussed that by changing by changing the charge trapped is the right word, because it's floating, it cannot go anywhere, trapped inside the floating gate, right? You can achieve, so by changing the charge you achieve either logic 1 or logic 0, right? Because you have certain amount of charge, you say, yeah, it is 1, it is, there is no charge or less charge, you can say it is 0, or either way, right? So basically, by controlling or having a sense of charge is something that you can talk about. Now the question is, how does one observe this charge there, right? Because you can, it's not like that you can go there and measure the charge in the floating gate. So you say, if it is a charge which is giving me 1 and 0, can I measure it? Can I measure the charge directly, so that I can know what is 1 and, right? And the answer to that is no, you cannot, because whatever we are measuring in as an electrical engineer or as an electrical person, you would do either voltages, currents, or your power, right? From that itself you have to conclude what is the charge or not. So then what is the property which, let's say, the floating gate charge can directly affect of my MOSFET? And it turns out that this is very much the property which we have also talked about in one of the video called threshold voltage. What is the significance of threshold voltage? Which is your threshold voltage. So what happens is, if you have more charge or less charge, depending on the charge, your threshold voltage would change, right? So the FG charge will change the threshold voltage depending on what kind of silicon you are having. Okay, but now you know that when the threshold voltage is changed, what would be the direct effect? If you apply a VDS for a different, for a given VDS, you are going to get a different IDS. So different FG charge, different threshold voltage, this means different IDS, right? And that is how one engineer can figure out from the current which is flowing through these terminals, oh yeah, this was 0 or this was 1. Interesting, right? Very interesting application of MOSFET, and it's very, 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 how do you see, prominent in these market. If you see, when we are talking about memory, you have probably heard of this flash drive, which we used to say the USB is typically the way it communicates. It's not the technology itself. The technology, which are in earlier days we used to call it EEPROM, right, which is the programmable memory, but now it can be called as the flash cell, right, and or the NAND flash cell, and I would come to why NAND flash. But it finds application in your drives, like your sticks, right, USB sticks, or you see it in the SSDs, which you find your for your computer, right? Not HDDs, SSDs, right? Which is the solid state drive. So that is the origin of, you see this so beautifully, that from the floating gate charge, or by trapping the charge, and that is trapping is obviously having by different VG, right? That's how you are changing the state of your memory, that how much charge you have in the floating gate. So now the question which I was saying is, this is the basic idea, that is what you see. But in current scenario, this structure looks very different, the way you see in the current products, and I'll come to that in a moment. But before that, I need to talk about, if you have heard this, that this is NAND flash. What is NAND flash? So you say, okay, why are you bringing NAND? Flash means this is the cell which is there. I do have this cell. Why do you say that this is NAND flash? So this cell is my flash cell, right? Why do you say that there is NAND flash? And that accounts for that we are not storing one bit here. We are storing a large data. Large data means, you have seen, as of now, probably you have seen the products for the SSDs or so, and you've seen easily your USB sticks or your SSDs are easily in TBs. TBs means terabyte. Terabyte means you are going somewhere 10 power 12, right? That is the range we are talking about. So now, to have that many cells, so each cell can give one bit or multiple bit. So let's, for now, let's consider that each cell is able to store one bit, right, which is what we know as the single level cell, right? So that means now, based on the charge, I could say, so let's say that means the high charge, a low charge would mean that you have 1 or you have 0. Suppose if you were having a capability where you could differentiate different charge based on the current, right? That means the different iota of charge, if you can differentiate, then you would say, okay, now I have a capability where I can differentiate the charge, or I would say this is the multi-level cell, where I say, okay, highest, let's say, for example, we could make, for example, 2 bits, 1 1, right? So this is the highest charge, Q max, right? Then you say Q max minus delta Q, which is, let's say, your 1 0, right? Then you say Q max minus 2 delta Q, which would be my 0 1. And similarly, this is the Q min, which I would say it's a 0 0. So based on which would be minus 3Q. So delta Q is the charge change in each state which you are having, and based on that you are getting delta I also, or delta VTH, right? And you can differentiate the current at the output. That means you are able to differentiate there is a change in the charge happening, and very reliably. Then only you would say, okay, I can make a very good cell. Because if you cannot do it reliably, then if you make an error there, it is can be 0 1 or 1 1. That means you have lost the data or information, or you have corrupted the information, right? So that is what a very important thing, that one can make multiple bit cell also using one, sorry, multiple level cell using one device. That means you don't need another device to make it. right? So that is the beauty which we have seen in flash drives. Beautiful, man. For me, this is a very, very interesting technology where we see 1 TB of that. So now let's go to what I mean by flash. So the obviously this cell or the symbol of this transistor I can show like this, right? Rather than I can show 3 lines here, right? So that you know that there is another floating gate which we are having, right? So this can be your gate source drain, and this is your floating gate, right? So that is the cell. Now people figured out that if they had, when they were trying to, let's say, make this memory, they had a configuration where you could put this like this, which you know as, you can guess already what logic I'm talking about when we are putting these things in parallel, right? So when we are putting these things in parallel, this is the resistor, this is, and this is, let's say, your one select line, which is, let's say, we are saying word lines, right, which are your select lines. So when you want to read any cell, you can read it independently, right? Because it can tell you, okay, how much is the change in your current. So let's say whenever you change the WL here, based on that, it would be able to, whatever state VTH it is in. So let's say, for example, this could be in two VTH, VTH1 and VTH2, right? So then it would be able to read which VTH it is because of the current which is flowing, which would be showing here on this voltage, right? It would go down or up depending on the, sorry, it would go down obviously, but it would go down by a factor in when you have a more current or less current, right? That is the idea. So that's how you are able to read at the output what is this voltage or what was this memory stored, right? So independently you can go in each cell because you can select each cell and you can do that. But what is the problem with that is that I need now to connect all of these cell, I need multiple lines. That means I need to connect the source of these, right? Suppose these are the drain of all, this is source of all cell. Then there are lines for gate which I would, this is in principle, this is a very good cell if I want to do a random access. Now this is again a random word which I'm using here, but you can google it if you want to. But simply, in very simple terms, it means random access is that I can randomly access any bit in my memory. That means if I want to go and check that cell, okay, what is the bit you have stored or what is the memory state you have stored, I can check that there. But what happens is, in this I spent, the problem which comes is the area penalty is high, right? That means if I want to make a 1 terabit, you can imagine how much area your chip will have, which would be probably of the size of the 2 3 laptops, right? Which you cannot afford. So area penalty is very high. So then people thought, is there a better way to pack this cell? And one structure which stood out is your NAND structure, where what is the beauty in the NAND structure is, right? So I'm just making 3. I'm just representing it with the resistor, but though obviously it could be any MOSFET, right? Which could be reading. So that means now I have this control signal, right? And then I want to read the state. But the problem here is, because each drain and source are connected of the MOSFETs, you see that what is going to happen if you want to read it, until these two are also on, you would not be able to read the state because it's in the NAND configuration. So the problem first is that random access is a problem, right? But what is the beauty of this is that when I put the transistors, let's say this is one transistor where I'm putting, this is another transistor. So I can then just put them in series to each other. It's very simple because I don't need to have another line coming and connecting, right? This is, let's say, the source line, but these are just connected to each other, right? So which reduces the area penalty and the footprint. So this is MOSFET 1, let's say M1, M2, M3, M4, like that you are putting in. So that means you can put them in like a battery pack, right? Like it looks like a battery pack or some container. So you see that the area is area is quite optimized, right? Area uses is optimized. So we can see that you can make multiple bits using this kind of configuration. That is what is known as NAND functionality. If you have seen these circuits before, if you have not, don't worry. We will talk about these circuits implementation in some other video, that what is this NAND NOR implementation in CMOS. But as of now, you can just see that this is the NAND configuration. If you have studied gates, this is the configuration, which is the NAND flash configuration, right? Now the last bit of this thing is, okay, good. So that means you are telling me these transistors, I could just put them on top, I mean, so, side to side to each other, and that can give me the density. But is this going to be the optimum way? Because I want to get 10 power 12 cells, right? Or at least if every cell is taking 1 bit. So that means, is this the way that I can scale? And then people figured out that because this is all, let's say you have this given area of the chip, right? So this is a chip area, and you are putting these transistors like this. You can only do so much, right? In a given chip area. So if you want to, let's say this is doing 1 GB and I want to go to 1 TB, you cannot say that I want a larger chip or my chip will increase. That is not acceptable for industry, right? So you are limited by chip area, right? You cannot have the more chip area. So how do you have the density? That is the question. And that is when you think, if you want to, at the same floor, if you have limited budget that you can only make one house or four houses, how do builder make money? They build on top of each other, right? So what is stopping me, that I have one transistor like this, I have another transistor on top of that, I have another transistor on top of that, and there are obviously here also. So let's say this is M1, M2, M3, right? This is M4, M5. So these are my transistor in vertical direction. If I can stack, then that would be beautiful to scale the density. So then this is the direction industry went, and this is known as, if you know, as 3D NAND. If you've heard of this 3D NAND flash, that means we are talking about 3D, so using the vertical direction, and NAND flash, obviously you saw the operation. So then now, how do you put a transistor? Because this looks like a transistor which can be only flat, but how we are going to put a vertical? And that is where you see that even the channel will go vertical, because as of now, what is the current flow is happening here in this direction, right, in the horizontal direction. But now if we want to make a vertical cell, then typically what you would do is, you have to reimagine the transistor. So transistor will become like this. Let's say this is your channel, for example. On top of that you have oxide, right? So this is your first layer of oxide, for example. Then on top of that you have floating gate, and on top of that you have another oxide, and then your metal, right? One, two, three. So then this is what, this is your oxide, this is what, second layer, floating gate. Then the third is your oxide again, and then for this your metal or whatever. And this channel is the channel. Typically, because we are only worrying about the threshold change, we don't worry about the current, maximum current which you come in. People typically use polysilicon also for the channel, right? And for oxide, it's the oxide which is needed. For floating gate, we use, which is a nitride layer, right? Because we need some layer which can trap the charge. Nitride is supposedly a good. So that's why this structure which we have, this three thing which you have see here, right? This is called ono. Ono means oxide, nitride, oxide, oxide, nitride, oxide, right? Nitride, oxide means you are having the oxide, floating gate oxide. That is the cell which is the key element or the heart of the cell, which is what it is made in this way. And now if I want to make on top of that, you see, only thing you have to do is just keep continuing these lines, right? So these lines will continue top to bottom, and then you can make different cell. If you can very selectively select a cell where you want to go. So you don't need to, the channel will go on, but your gate, which is there, is only this. So this is your word line. Let's say this is word line 1. Similar to that, you will have word line 2 coming in here, right? You can check out this structure on the web, 3D NAND. If you type, you will get. Similarly, this structure will continue. Then you will see here, let's say word line 3, right? So that is one way you can see that you can put them on top of each other, and you can make these cells, which are the your building blocks of whatever flash drive SSD you are carrying, right? So that is the most beautiful way I have seen this utilization of the way industry is thinking. I mean, it's just mind boggling. That's why I say that semiconductor industry is very, very bold industry. Though it takes time to make a technology qualify because of the challenges, but it's a more sophisticated industry. And if you want to understand and work on challenges, I think there are plenty of challenges in this industry which can drive, because it's not going to go away, right? I mean, it's going to just, the things are getting just started with AI and all those things. So that is what you would see, that this is a very interesting element. Now we have to think, how can we continue in the future if we want to go? What is the way? Because we are utilizing the vertical direction. What is the other way, right? If do we put multiple dies on top of each other, or what do we do if we want to increase the number of cells, right? So that would be something which on the red roadmap you can already start thinking that what would we do. With that, I would end here, and happy learning to all of you. I hope you learned a little bit what is inside your flash drive, and this is this stack of these devices which are inside your flash drives. Okay, so that is what it is, and it is very much the cousin of the MOSFET which we have seen, because it does have oxide metal, thus that it has extra layer which is the floating gate which is trapping the charge, and then other things are very similar to MOSFET. Thank you. Happy learning. Keep growing, everyone. Bye bye.